At first, this question doesn't seem like anything to do with the optimization question, but if you think about it, let's see, what is this? If you plug in 0 for y, you get 2x equals 12. So that 6 is your x-intercept. And if you plug in 0 for x and solve for y, you get 3. So 3 is your y-intercept. It's a straight line going through there. And we're looking for this distance, right? Distance from the origin to this line. At first, it doesn't seem like anything to do with optimization question until you realize that, well, among all the possible distance from a point on this line to this origin, the distance from the line to the point is considered to be the shortest distance between a point on this line to the origin. Is that right? Yeah. So this question can be put into the following scheme. You can say, if I take the function f x comma y as x minus 0 squared plus y minus 0 squared, which is like the point distance between the points x comma y and 0 comma 0. Under the constraint, what's a constraint? The constraint is that the points that we're considering should be on this line, right? With 2x plus 4y equals 12. That's our constraint, right? So we're trying to minimize this under this constraint. That's the question. All right, how do we do this? Well, we have to minimize this function so under this constraint, so we're just going to use the Lagrange multipliers. However, trying to use this entire function to be f is not a good idea, because if you differentiate with the square root, it's very complicated, right? So what would be a good method? What should we take as the target function to maximize or minimize?
It's under the square root.
The thing inside the square root, we're just going to call this h of x comma y. That's just x squared plus y squared. And just notice that if this is maximum, f will be maximum. If this is minimum, this will be minimum, right? So we just have to figure out when this is minimum under this condition. That's all we have to do. Not easier, right? Good. So now let's compute gradient of h, which is 2x, 2y. And then what's the gradient of our constraint g? What's the gradient of this? 2, 4. Where should I multiply lambda? This one, right? Because that one doesn't have anything, so it's easy to put lambda here. So we're going to say 2x, 2y equals to twice, no, lambda times 2, 4, so it would be 2 lambda, 4 lambda. So that you have 2x equals to 2 lambda, 2y equals to 4 lambda, which gives you that x equal to lambda, y equals to 2 lambda. Now what do you do after this? You have to consider your constraint as the third equation, right? So once you solve the Lagrange multiplier equation, always go back to your constraint and use that. If you solved the Lagrange multiplier problem without using the constraint, you're doing something wrong, okay? You have to make sure that this is satisfied. So let's plug that in here. Let's see, you get 2 times lambda plus 4 times 2 lambda is equal to 12. There's 2 times lambda plus 8 lambda equals to 12. So that's 10 lambda equals to 12, giving you that lambda must be 12 over 10 or 6 over 5. And then you can plug it back here to get the x values. You get x equal to 6 over 5, and y equals to 12 over 5. And now we have figured out when it attains its minimum. So now you go back and plug it in here, and that's your answer, okay? F at 6 over 5, and 12 over 5. Square of this is 36 over 5, 25. 144 over 25. So that's square root of 180 over 25. Well, taking the square root top and bottom, you get 6 radical 5 over 5. So that's the answer. That's the distance from the line